The next kind of distribution we're going to discuss is something called the normal distribution. The normal distribution is probably the most common of the probability distributions, and, in my mind, the most fun. So the normal distribution, by definition, is the probability of selecting a variable in relation to the mean. So we've all seen, over the course of our time, this graph is called the bell curve, and this is called a normal distribution. That is, if we take a line down the center of this distribution, the mean, the median, and the mode are exactly the same. That is, the mean is in the middle of this distribution, the median is the halfway point. So if we were to divide this in half, 50% of our values are on this side of the line, and the other 50% are on the other side of the line. And this is a very important point, and we'll want to come back to this later. In addition to this, we look at how many standard deviations from the mean any item is in our distribution. And so typically, in this normal distribution, we have what's called 1, 2, and 3 standard deviations from the norm. And as you can expect, to the left, we also have -1, -2, and -3 standard deviations from the mean. So this would be +1, +2, and +3 standard deviations, -1, -2, and -3 standard deviations. Because of the shape of this curve, we can expect that in our distribution of values, 68% of our data will be between +1 and -1 of the mean, 1 standard deviation of the mean. 95% of our values are between -2 and +2 standard deviations, and 99% of our values will occur between -3 and +3 standard deviations from the mean. What you see then is that this line continues to extend, and this curve keeps on coming down, but it never quite meets this bottom line. And so, but in effect, between here and here, these values only represent 1% of all of our values. The key thing to remember, though, is that to the left of the mean, we have 50% of our values, and the other 50% of our values fall to the right of our mean. When we're working with a normal distribution, we create something called a z-score. And a z-score is just a way to standardize a distribution so that we end up with that normal distribution and with the mean, median, and mode. So later on, if you get into statistics, this is a way to help you compare two groups that are of different sizes and different means because you normalize them. But in this case, we want to find out the probability of selecting a value from a group of values that is greater or less than the mean. So we're going to take a series of steps, and the first thing we need to do in order to determine this probability is determine the z-score. Now we can do this in Excel, but I want to walk through it using a formula first, and the formula is actually pretty easy. So I want to do this just to help us understand let's do another page here. The formula is z equals x minus mu divided by the standard deviation. So we talked last week that the mu is the notation for the mean. So we have a set of data, and we know what the mean is of that set of data. We can also calculate the standard deviation of that group of data. So let's say that, for example, we had a group of data, and the mean was 100, and a standard deviation is equal to 15. What's the probability that of these, all this data, that if we were to select somebody, that person scored 130. Let's say that the average score was 100. We want to know the probability of selecting someone who got at least 130 on the test. So if we were to do this as a normal distribution, this is the mean, this center line. And so we know that 130 is greater than the mean. So we want to know the probability of someone scoring up to 130. So let's plug in these numbers. So z equals 130 minus 100 divided by 15. So z equals 30 divided by 15 equals 2. The next step is to take that z-score and identify the appropriate probability or the related probability. So in your Inkling chapter, in your Inkling book, in table E2, there's a chart, and across the outside of it are z-scores, and you'll see a series of z-scores running down and across. And then in the middle of these, you see some probabilities associated with those z-scores. So, for example, if you end up with a z-score of 1.0, you come down the left-hand side of the table until you get to 1.0 and go over to the first column, which is 0.0, and you'll see a probability of 0.8413. If you were to have a z-score of 1.75, you would come down here on the left until you get 1.7, and then at the top, one of your columns is labeled 0.05, so you come down till you get to 1.7, come down till you get to 1.7, go across until you get to 0.05, and you'll see a probability of 0.9599. So what this means is that if you have your probability distribution and you have your mean, and in this first case, a z-score of 1.0 would mean that you would be exactly one standard deviation away from the mean. And the probability of selecting somebody 1.0 away from the mean is all of this. So that would mean that 0.8413% of your values falls between one standard deviation from the mean and less. I'm running out of colors here. Similarly, if you end up with a z-score of 1.75, that means that almost 96% of your values fall between the lower end and 1.75 standard deviations. So let's do a sample exercise. Haynes Construction Company builds primarily 3- and 4-unit apartment buildings called triplexes and quadruplexes for investors. And it's believed that the total construction time in days follows a normal distribution. The mean time to construct a triplex is 100 days. And a standard deviation equals 20 days. Recently, the president of Haynes Construction signed a contract to complete a triplex in 125 days. Failure to complete the triplex in 125 days would result in severe penalty fees. What's the probability that Haynes Construction will not be in violation of their construction contract? So we want to have x equals 125. So if we were to draw this graphically, the mean equals 100, and x equals 125. We want to know what the probability is that we're going to not complete that triplex in 125 days. So let's first plug our numbers into the formula. Remember, the formula is z equals x minus mu over the standard deviation. So z equals 125 minus 100 over 20, which gives us a z-score of 1.25. So the next thing we need to do is figure out what the related or the associated z-score is, or the associated probability is for a z-score of 1.25. So I'm going to pull up a screenshot of our table. And again, we're going to come down the left until we get to 1.2. And you can't see this on this, but the top of this is 0.00, 0.01, 0.02, 0.03, 0.04, and 0.05. So we come down till we get to 1.2, and then we come across until we get to 0.05, and so the probability is 0.8944. So that means that there's a pretty good chance, almost a 90% chance of not violating the contract. So again, if this is our distribution and our mean is 100, and we were interested in 125 days, that 89% represents 0 through 125 days. So let's look at it from a different question. If the firm finishes the triplex in 75 days or less, it's going to receive a bonus. So what's the probability that Haynes will receive that bonus? So let's just do this curve again. Again, the mean is 100. And now we're interested in 75 days. And so we're interested in this part of the curve right here. So let's plug our numbers in again. Z equals x minus the mean divided by standard deviation. So 75 minus 100 divided by 20. And this time would get a z-score of minus 1.25. So let's pull up an image from this table again and figure out what our associated probability is. So this time we're at negative 1.2, so we're going to come down our table until we get to negative 1.2. And again, let me label these really quick. So I'm going to come down until I get to minus 1.2, come across until I get to 0.05, and I end up with a z of minus 12.5 equals a probability of 0.1056. So the probability of completing this triplex in 75 days or less is 0.1056. So that represents this part of the chart. All right, so let's do another example. An industrial oven used to cure sand cores for a factory manufacturing engine blocks for small cars is able to maintain fairly constant temperatures. The temperature range of the oven follows a normal distribution with a mean of 450 and a standard deviation of 25. Leslie Larson, president of the factory, is concerned about the large number of defective cores that have been produced in the past several months. If the oven gets hotter than 475 degrees, the core is defective. What is the probability that the oven will cause the core to be defective? What's the probability that the temperature of the oven will range from 460 to 470 degrees Fahrenheit? So let's do this in two steps. The first question, what's the probability that the oven will cause a core to be defective? So we're looking at an x of 475, because that's the temperature at which the core gets defective. So this is our mean. So we're going to take 475 minus 450 divided by 25, and that gives us a z-score of 1. We know from earlier, when we had a z-score of 1, that the probability associated with that z-score is 0.8413. But we're not quite done yet, because that 0.8413 represents this part of our normal distribution. The question is asking us what the probability of problems if the core is higher than 475 degrees. So we're interested in this piece of the chart. So if this is 84%, then this equals 1 minus 0.8413, which gives us a probability of 0.1587. The second part of this now asks us the probability that the temperature of the oven will range from 460 to 470. So in this instance, the first thing we need to do is do two calculations. So the first one, we're going to use 470. 470 minus 450 divided by 25 equals 0.8. 460 minus 450 divided by 25 equals 0.4. The probability for 0.8 equals 0.78814, and the probability for 0.4 is 0.65542. So we know that the probability associated with 470, an x of 470 is 0.7814, so that represents all of this. That's 78% of the chart. The probability associated with 0.4 is this piece right here. But we're interested in this piece. So in order to calculate that, given these two numbers, we subtract 0.65542 from 0.78814, and we get an answer of 0.1327. Okay, let's do one more example, and then I'm going to show you how to do this in Excel. All right, Steve Goodman, production foreman for the Florida Gold Fruit Company, estimates the average sale of oranges is 4,700, and the standard deviation is 500. Sales follow a normal distribution. So A, what's the probability that sales will be greater than 5,500? B, what's the probability that sales will be greater than 4,500? C, what's the probability that sales will be less than 4,900? And D, what's the probability that sales will be less than 4,300? So pause this video, solve the problem, and then come back and I'll show you the solution. Okay, let's tackle the first one. A, we want to know the probability that sales will be greater than 5,500. So let's draw this out. We know that our mean is 4,700, and our standard deviation is 500. So we're going to take 5,500 minus 4,700 divided by 500, and that gives us a z of 1.6. So the associated probability for 1.6 is 90.9452. So that represents this. But the question is, what's the probability that the sales are greater than 5,500? So we are interested in this part of the curve. So in order to get that, we take 1 minus 0.9452, which gives us 0.0548. So the probability of our sales being greater than 5,500 is about 5%. Okay, the second one. What's the probability that sales will be greater than 4,500? So again, our mean is 4,700. 4,500 is somewhere here. And we're interested in greater than 4,500. So we're going to take 4,500 minus 4,700 divided by 500. And that gives us a z-score of minus 0.4, which gives us a probability of 0.65542. All right, next. What's the probability that the sales will be less than 4,900? So we're interested in this. So we take 4,900 minus 4,700 divided by 500. That gives us 0.4. And then again, our probability then equals 0.65542. Finally, probability that the sales are less than 4,300. Minus 4,700 divided by 500 equals negative 0.8. That gives us a probability of 0.21186. So that is normal distribution calculated by hand, and let's do it by using Excel. The command in Excel is norm.dist. So the first number that we type in is x, followed with a comma, and then we insert the mean, and then the standard deviation, and then whether or not it's cumulative. And most of the time for these, you put in true. So let's look at the previous problem where we were looking at what the probability of sales less than 4,900 when the mean equaled 4,700, and standard deviation equaled 500. So in Excel, you type norm.dist, parentheses, 4,900, comma, 4,700, comma, 500, comma, true. I ran out of room there, sorry about that, and close parentheses. And when you press enter, you should get the same answer, 0.65542. So we took the long way to get to this very simple Excel formula, but I thought it was really important for you to understand how we got to this number.